So this is a video, chapter 13 again, continuing discussing making a solution. So when we're talking about making a solution, yes, we are going to talk about delta H, but something else we're going to be discussing a little further on down the line, but it's brought up here a little bit, is something called entropy. And it is a capital S. It is disorder of a system. Now, of course, we're going to be looking at the change in S. How much does it change compared to beginning the reactants to the products? So similar to what we've done with thermo. So it's disorder of the system, chaos of the system, however you want to explain it. So it turns out the more disorder you have, the more favored the process is. And what we talk about is something called spontaneous. So if a process is favored in nature, it is spontaneous. So we're going to be using those terms as we go forward. So in terms of solutions, okay, and that's what we're focused on in this particular chapter. So again, we're going to come back to entropy, and I'll kind of mention it a little bit more here. If I take two ionics solids, sodium chloride versus calcium chloride, and you see that they break up into, this would be calcium, as A+2. I have 2 ions here, and I have 3 ions here, okay? So the one that has more ions is going to cause more chaos. So this is going to have a higher entropy than the sodium chloride. And this is going to be something we talk about with colligative properties and how it affects it. So not only are we looking at a delta H, we are going to be also looking at what we call delta S. And the combination of the two is going to give us something called delta G, which is Gibbs free energy. And that's what we're going to talk about later on in chapter 19 and 20. So delta G is really the combination of, is it exo or endothermic, and do you have an increase in entropy? Now the increase in entropy is going to be multiplied by temperature, because if I have entropy, if I have an increase in entropy, I probably have an increase in temperature. So think of, again, gases in a box. If I increase their temperature, you're going to have more and more chaos in there. So same kind of idea. So if I'm looking at the overall delta G, I'm looking at the combination of both the entropy factor and the heat. But again, this is just a preview for what we're going to see later on. But I still like to bring it up because it does have to do with number of ions. It does have to do with number of ions. So speaking of dissolving and affecting how things behave, we're going to talk about factors that affect solubility. So we're going to talk about gases, and we're going to talk about solids. And how they can change their solubility depending upon the situation. So in terms of gases, that's what I'm going to talk about first here. Gases are going to be, of course, affected by pressure, okay? So pressure in our case, we're talking about trying to dissolve a gas into a liquid, okay? And I'm going to use the idea of carbonated beverages for this one. I'm increasing the pressure above the liquid, so write down increase in pressure above the liquid is equal to the increase in the solubility of the gas. So thinking of a carbonated beverage, as someone has expressed that if you are making a can of Coke, you have to put that can of Coke up like 5 times atmospheric pressure in order to push the CO2 into solution. So we have to put some pressure on the gas in order to get it to dissolve. So there is a law associated with it. It's called Henry's law. I'm not going to spend too much time on it, but he found that the amount of gas is directly proportional to the pressure above the liquid. So as you increase the pressure above that liquid, okay, you could get more gas to dissolve. So you could increase the concentration of the gas. So again, Coca-Cola Company, they have a certain patent on how much CO2 they have dissolved in their Coke syrup. That is going to be how they manufacture it and change the pressure on the outside of the container in order to get the CO2 to dissolve. So I always imagine it as a CO2, you're trying to drown the CO2 in the water. Not a good image, but it is a way to kind of imagine pushing it down. So we can, the actual Henry's law is solubility is equal to a constant times the pressure. So solubility of the gas is Sg, and it is in molarity. K is a constant, moles over liters times atmosphere, and this constant does depend upon temperature, So again, the CO2 is trying to get into that water, so depending upon what the gas is, and that constant is going to be directly related to the gas, you're going to get more or less to dissolve in there, So we are going to talk about, so that's gases. So gases have to do with pressure, but we're also going to deal with temperature. We're first going to talk about temperature in terms of solids, So if you have this graph here, okay, this is a graph of different solids, and it's looking at temperatures. Okay, so these are mostly ionics. I think they're pretty much all ionics. And there is a line indicating their solubility. So temperature is in Celsius, and this is solubility is in grams of solute per grams of water. Okay, so solubility of solids is always given in grams of solute per 100 grams of solvent. Okay, that is how we do solubility of solid. Again, the reason we need to have a constant on the bottom is because if we have more solvent, you're going to get more to dissolve. So that is why you always need a constant. So it's out of 100 grams of water. So this is called the solubility curve for the solid. So let's specifically look at the line here. That is potassium nitrate. Okay, that's the line there. So each one of these lines is associated with each. So as you could see generally, for solids, if you increase the temperature, you're going to increase the solubility. Okay, in general. Now you do have some ones that are going down. You have some that are kind of straight across and not really changing. And definitely some are decreasing as you increase temperature. But we're going to always assume that as I increase temperature, I'm going to get more to dissolve. So anytime I'm making a solution and I can't get it dissolved, I sometimes put it on a hot plate to see if I could get more of it to dissolve. Now the line itself is something that we call saturated. So that means that is the maximum amount of potassium nitrate that I could get in there. So if I look at 60 degrees Celsius, it's somewhere above 100 grams I could get in there. So that means that line is telling me I can't get any more in there. So there's three terms that we use to describe solubility of solids, okay? One is called saturated. That means all of the solute has dissolved, and that is what the line is. Okay, so the line is telling you that point of saturation. Okay, so think of water. As it rains, there's always a saturation point, and then you start to get puddles everywhere. Unsaturated means more solute can be dissolved. Okay, now technically speaking, that's going to be anything underneath this curve. So that's unsaturated. Is any place below that. So if I'm at 60 degrees Celsius and I have 50 grams in there, that's considered to be unsaturated, meaning I can get more solute that can go in there, more solute can be dissolved. And then finally, this weird one is called supersaturated. More solute is dissolved than expected. That's going to be up here. Okay, so this is supersaturation point. Okay, supersaturated. And please note that how you attain that is you take something to a very high temperature and then you cool it slowly so that if you get it to 20 degrees Celsius and you have 150 grams in there, you're going to be at a supersaturation point. And there's an interesting video that I'll kind of link up so you could kind of see supersaturated. So to kind of finish up this idea of saturated and unsaturated, the only way you could tell a solution is one of these is by actually interacting with the solution. So if you want to draw three beakers underneath the graph that we were just looking at, if I drop a solute into an unsaturated solution and I stir it up, I will see that the solid dissolves. So what I'm trying to show in this picture here on the left is that there is no solute in there once you mix it up. If I have a saturated solution, which is the middle picture, and I dump some solute in there, mix it up, what would happen is that solute falls to the bottom here. Okay, so that's what I'm trying to show in this picture, little dots there. So that solid didn't dissolve because I've had that, I'm completely saturated, so no more of it can go in there. And then the video I want you to watch is supersaturated. This is very weird. So again, supersaturated solutions are very unstable. So if you put one more crystal of solute in there, what it turns out is it all goes back to solid, okay? Pretty instantaneously. So if you watch that video, that's what you're seeing there. It's very, very strange phenomenon that you have. All right, so finish up one more thing. If you go to this graph is looking at gases and temperature, gases and temperature. So again, you will see that temperature here is on your x-axis, and then solubility is over here on your y, and you might see it listed as milli molarity because of the fact that gases, you can't get much to dissolve. That's why it's in a lower unit. So if I take methane and try to dissolve it in water, oxygen, carbon monoxide, or helium, and I'm trying to dissolve it, typically gases, as I increase temperature, you're going to have less solubility. And that's generally because the gases are going to want to escape that liquid as you start to heat it up. Because gases, again, will always are going to increase their kinetic energy a lot easier than anything else. So therefore, you're going to get more to escape because